So this first session will be an intro to OriginTrail. And we're going to start somewhat high level, and then we're going to dive into the main elements of the DKG. Why are we here? Well, one of the problems we're trying to tackle is using AI in a safe way, in a reliable way. We talked about that yesterday quite a bit. I like these two examples just to show, to start with, because they show some very weird behavior by Gen AI today. And this behavior is, something that we're kind of taking for granted, and is also something that is a major blocker for AI being really used in the enterprise context especially, but also in general, in some sort of reliable way where you can really trust the system and you build it with it so that you're sure that it will do what you want. And basically, you probably even heard there's this statistic that 95%, MIT published, that 95% of all the enterprise pilots or projects basically fail. So this is one, if not the main reason, one of the main reasons why this happens. But this type of hallucination that we've seen is really kind of a feature. These LLMs are really good guessers. So actually, let's do a wake-up exercise. We did this in previous DKGcon. I love it, so let's do it once again. When I point to you, you should say a word that basically continues the previous array of words you heard, and say it out loud. So I'll start with you. IB, okay. Okay, IB. I am, okay. Yuri.
Yeah, I am A.
I am A.
Guitar.
Guitar. Music. I am a guitar music. Okay. So let's say we heard a sentence here that everybody tried to connect, basically invent a word that somehow connects with the previous sequence of words or a sentence. And we didn't really get to the best sentence ever, but essentially, this is how LLMs work. Like the next token is predicted based on previous tokens, and these tokens, we can basically kind of consider them words. They're just like pieces of words. But essentially, through this mechanism, now we're trying to solve everything. We're trying to solve physics. We're trying to generate images, things like that. It kind of naturally and intuitively feels that this is not a way you do math, for example, right? So therefore, we believe hallucinations are a feature. Not saying that this is a bad thing. Like the LLMs are super creative. This was incredibly creative. But it's not super reliable. So that's one of the problems. The other problem that obviously we've been talking about a lot yesterday is data ownership, intellectual property, who gets to own this, which is very often coupled with centralization. Should we put all of our data in one place? Obviously no. At least at this conference, I'm pretty sure nobody believes that, because that also further introduces bias. So whoever controls information and the filters through which we see this information can introduce a lot of bias into the system and the world in general. And another thing that we talked about yesterday quite a bit, as we have more data generated by AI, that data, because quite often you don't know it was generated by AI, it just ends up on the internet. They say that actually Reddit is more AI bots than people right now. They say because we don't know. We cannot really reliably know. But people do use that data to train models. And when that happens, it turns out that models start to deteriorate. So you're expecting that you give it more data, more new data, and it's going to become better because you're going to have more knowledge. But actually, it turns out it becomes worse. And I'm no expert on this topic, but you can look it up. There's a bunch of research papers, and it's quite a new thing. So it seems, and it kind of intuitively makes sense that if we start producing things like this, and this ends up training AI, will AI know better what a bicycle is? I don't think so. So anyhow, these are some of the problems, what we expect to happen. And this is, again, not just us, but also folks for Google DeepMind, particularly Turing Award winner Richard Sutton, is that we kind of are going through now a third phase of AI. The initial phases were these simulation phases. So we had AI that was great at playing games, like, for example, chess or Go. it's interesting, I believe it was, what, the 90s, when Garry Kasparov was beaten by IBM's Deep Blue, maybe 97. Yes, thank you, Professor. But essentially, chess is kind of an easy feat for AI because it's a quite small world game. There's not that many moves for a machine. So when it plays against a human, it's able to pre-compute all the possible moves from the current state of the game and always pick the best one. And then whatever human plays next, it computes everything again, and basically it's always going to beat you because it's mathematically easy to do so. What was actually interesting when they got into this alpha Go phase, the Go game, turns out that there's so many moves in Go that there's not that many atoms in the universe. So it's quite a complex game. You cannot pre-compute everything all at once. So the AI had to be a bit more clever. So they introduced this notion of learning into the whole thing, but it was still a simulation of a game. And at some point, it kind of topped off. We got into the phase of deep learning. We got things like GPT, which are incredible. I'm sure everybody here uses it, or some form of LLM. And the idea there was, let's not teach it rules. Let's feed all of the data inside and do a bunch of very clever stuff, but ultimately create these prediction machines. And that's what they call the era of human data. And we're kind of exiting that era because we consume that data. We're producing a lot of LLM-generated data, and it looks like kind of that idea is exhausted in a way. What they see is that we get into era of experience where now we actually will have agents who will, just as we humans do, learn from their experiences. So they will try, just like a child learns to walk, it starts and then it falls a little bit and then moves around and it starts learning from that, or whatever kind of other action we do, through this feedback mechanism, through some sort of reward and reinforcement of behavior that brings us rewards. And they call this the era of experience. So the idea here is that we move into a stage where it's actually agents learning and putting a bunch of those learnings in their memory, so not actually training the LLM. And that was also discussed yesterday, and I truly think we covered that topic, so I won't go too deep into it. But think of what we're building today as essentially the enabler for that to happen. So basically, when we talk about agents, we can think about three things that are important here. They have some system that they are in, so their domain of agency. They interact with some world. It can be totally digital world. It can be like an agent on Twitter, for example, that you built with Eliza OS and it talks to you. Or it can be in the physical world. Whatever the domain of agency, it's a factory, maybe a building. And in that way, it interacts with maybe other agentic or non-agentic systems. We have some AI model. Doesn't have to be a Gen AI model, but whatever kind of AI model is going to do a bunch of clever stuff, right? Natural language interactions, is going to be thinking, is going to do RAG. And then the idea is that we have this memory. And then in the memory, we have experiences that are recorded, including the outcomes of what, so basically attempts, I'm trying this, that happened. So, they can learn and they can reinforce those learnings. So that is kind of the new thinking. Instead of stuffing everything inside of the LLM, we have this external memory where we can go as an LLM or an agent and fetch what we need. So having that said, what kind of agents are we looking for? Basically, ideally, we want to have reliable reasoning, so no hallucination, if possible. We want to know, for all of this memory, where does this information come from? What did the system interact with? And what is the source of the information? So basically, source, reputation, and provenance of the information. Obviously, as we discussed, we don't want centralized value aggregation only. We want people and agents in this arena to have some form of fair value exchange and that we incentivize the right behavior. Yesterday, we had some good talks about how social media was incentivized to push certain content to you to keep you more engaged, to basically get you to doom scroll, right? Which is not necessarily aligned with what we would like as humans, right? It's kind of sort of a narcotic technology approach. And do we really want to go into a world where everybody's sort of in this narcotic relationship, or should it be the other way around. Should it be that the technology improves us and teaches us more and helps us? I believe the latter. So in a way, the incentives should go there. We want obviously multiple data sources, so agents exchanging and systems exchange information, somehow retain data ownership, and obviously privacy. We don't want to just reveal everything. That would not be a good idea. So one way to look at this is also through this analogy of we've been speaking about previously, I don't believe yesterday though, but the one of the brain. I think Ben was mentioning a couple of times. Or basically you can think of it as kind of a left and right brain analogy where the left one is really the rational one that kind of, at least we see that a lot as a kind of an analogy, and then the creative one is the right one. And so basically on the left side, we want something deterministic, we want some sort of logical reasoning, rule-based inferencing, some sort of trusted execution, and that's the domain of the DKG. So we finally lock into the DKG. On the other side, we basically have generative models and on wider AI models that are not rule-based, they're more statistical, probabilistic, and their execution is not as trusted, as rigid as something that I'm going to go deeper into. But like, again, Ben mentioned yesterday, have this way, they're kind of like a human. If you ask a question 2 times in the span of 2 years to the same person, you're probably not going to get exactly the same answer to that question with the exact same words. That's how we interact with specifically Gen AI models today. But if we combine these things together, they have a potential to cancel out each other's flaws. So essentially, when you do this, you get this neural AI, which is this right side, this neural networks, and this symbolic AI, which is actually an older branch of AI, which knowledge graphs fall into, which is all about facts and rule-based reasoning, and symbols representing the world not as like neurons with weights, but rather with certain symbols that that you can reason with, and I'll explain that now in further depth. And you get this notion of neuro-symbolic AI, which is really the next frontier of AI, and you've been hearing a lot about that yesterday. Welcome back, Ben. I was hoping you get to see the brain because you were really enjoying it yesterday. So, yes, polished up and nice. So yeah, that took about 15 minutes, so I hoped it was quicker. So I'm going to go now and explain how we go into what are these key basic elements of knowledge graphs and some key concepts. We cannot dive too deep into every one of them, but we're going to skim over it, and if you guys have any questions, just interrupt me at any point. But essentially, we're going to dive into the left brain now, so into how can we do this reasoning, how can we model the world through knowledge graphs. And we're going to start extremely basic. Oh yeah, I forgot to mention, so I said neuro-symbolic is the new thing. There's a ton of research coming out. So just a couple of papers I picked up over the last few months, but they're like literally weekly, a couple of really, really interesting papers out there. So it's worth looking into if this sounds exciting to you, because there's just like a booming amount of new knowledge and experiences coming out. Okay, so when we think about the DKG, we should think about it in terms of 3 layers. We have some sort of agents on the top layer, in the agent layer, and the idea is we have more agents. And what we really want to give them is this trusted memory, which is the bottom 2 layers, so specifically the knowledge layer, which we see as this semantic graph, and I'll explain it deeper. It's a semantic graph of knowledge, ownable knowledge assets that originate from multiple sources. Now that's a mouthful, but we'll explain like literally every single word in that sentence throughout the following slides, so bear with me. And then there's the trust layer, which is actually implemented on blockchains, because they're the most trusted type of, let's say, a trusted execution environment. And they're widely used for implementation of ownership, tokenization or monetization, provenance of transactions. So we'll be diving a little bit into that too. So basically, in this presentation, I will now dive into the bottom two layers a bit, knowledge and trust layer. I won't go too deep into the agent layer, but in the next sessions, we'll touch upon that, and especially Shaw will give us the best out of it, way better than us in this, so he'll I'm sure rock it with what he has to show. Awesome. So let's go knowledge graphs 101. You ready? Okay, super simple. Why are these knowledge graphs so great? Well, generally, when we think about data, there's actually, maybe I should show that. I don't have it in the slides, but there's this notion of, yes. So this thing is a kind of a representation of how to think in terms of hierarchy. This DKW pyramid basically illustrates that we have some type of raw data at the bottom of the pyramid. It's quite unstructured, unlabeled. You know, it comes out of sensors. It comes out of all over the place. If you give it some context, if you package it up a little bit, you get to information. So let's say data would be number 15 coming out of some sensor. But you kind of have to know that that's a temperature sensor, maybe. So when you assign, 15 Celsius from this temperature sensor, okay, that's already information. Before that, it was just some number that you couldn't really, what is it, 15 people, 15, degrees. And then when you get to the level of knowledge, you add even more richness and context to that. So basically, you would describe this sensor and this, what a Celsius is, and you would dive really, you will make it very rich, and I'll explain it in the next slides. Ultimately, reaching this peak, the wisdom, or we could say intelligence, which basically uses the bottom stuff. But what I'm trying to point at here is that not all data is knowledge, and not all knowledge is data. And now we're going to see what that means. I hope on the rest of these slides. So what we specifically consider knowledge in knowledge graphs, the minimum sort of entity, the minimum thing we have in these graphs are literally entities and certain relationships between them. Entities can be any kind of object. If you've done any sort of object-oriented programming, this notion of objects and classes, that's kind of it. And the idea here is that you can represent everything in the world in the form of what we call triples. So two entities and a relationship. Or another way to say this is subject, predicate, object. DKGcon is in Ljubljana. That's two entities, DKGcon, Ljubljana, and there's a relationship that one is located in Ljubljana, let's say. Or the Christmas tree is green. That's an object that has a relationship with some property. Green is not really another object, but this would still be a triple. So there's ways to different ways to observe this, but ultimately that's kind of the thing. It's different from, let's say, your key value store, where you have, I don't know, temperature 15. Okay, but of what? So basically the idea here is that you have these triples or even more. Sometimes we have something we call quads, which is structures of 4 that are richer than key value, and therefore we can make actually very interesting graphs out of them. Now, I like to also start with this distinction that there's kind of a schism in the knowledge graph world, and people quite often come into one of the two camps. There's a property graph camp, and there's like a knowledge graph camp. Also talk about that yesterday. But basically, it comes down to kind of the same concept. It's the same concept, but done a bit differently. And both things have their place. One is, let's say, more, one is better than the other in certain things, right? So you might want to pick one or the other depending on what kind of things you want to build. When we think about this at OriginTrail, we try not to be opinionated. We want to be inclusive, as we discussed yesterday. So we like to start with standards. And that, therefore, DKG adopts the W3C semantic web stack, which is a set of standards that's been around for a very long time. And actually, if you heard of the term semantic web, that's where the knowledge graphs come from. The term semantic web is effectively the first time people started talking about Web 3.0. So we in the crypto world, we consider Web 3 today as read-write-own web. But actually, back in the day, the person who invented the World Wide Web, Sir Tim Berners-Lee, he invented the semantic web as a improvement, or in his words, Web 3.0 at the time. So if you ask somebody in like 2000, year 2000, that would be like basically Web 3, they would think about the semantic web. So which is an interesting coincidence because we're today at both of these worlds. And here basically that's what I'm pointing at is there's been a lot of time and research invested into how to do these things well. So we decided to obviously pick up on that and build on the shoulders of giants like Sir Tim Berners-Lee and the rest of the folks who've been involved in this for so many years and made all the mistakes so we don't have to. So basically what we'll be talking about is RDF, or short for Resource Description Framework. And a resource, when we say a resource, we kind of think of this entity. And then there's a Sparkle query language, which is effectively kind of like SQL. It's like SQL for graphs. We'll be seeing a lot more about that today. So basically, what you need to take away from this is a graph is, at minimum, there's like two things and some relationship between those entities. So let's have an example. If Socrates is human, those are two things. Human is a concept, it's not a thing actually. So we can also make relationship not just between entities that are physical things or instances of something, we can also put concepts inside of this graph. So if Socrates is human, we can note that down in various ways. There's one notation called turtle, which looks kind of like this. Socrates type human. There's these X things in the beginning, but I'll deliberately wait and tell you more about that later. There's another way to write this down, which is JSON LD, or JSON for linked data. The reason this was invented because a bunch of these notations, like turtle, and there are other ones, there are quads and N3 and a bunch of, so people have been creating these ways to write down graphs in text called serializations effectively. And at some point they realized, oh my God, this is so complex and weird. We need something that people understand. So basically they said, okay, everybody uses JSON. Let's make some form of JSON notation. And they invented this JSON LD notation. And effectively, it looks a little bit richer, but it defines some object ID. So in this case, we have this @ID thing that you normally wouldn't see in a JSON. It has an @context, which I'll explain a bit deeper, but it gives you basically some sort of way to represent the world that is ideally shared or standardized among others. And this context basically here says, okay, we have this idea of something being a type. So basically that type here, we now can relate to this thing here, which is some sort of RDF type. I'll go a little bit deeper into it. But long story short, it's not easy to write down a graph in text. But essentially, what you're seeing here is a triple, and there's different ways to do it. There's even a very cool website, which we'll hop on in a few slides, that you can play a little bit with this, just get a feeling for it, which is called JSON LD Playground. But yeah, it was basically a bunch of academics did a bunch of really cool but very complex ways to note down graphs, and then somebody came about and said, we need JSON. So actually, when you're using the DKG, we went this route as well. So JSON LD is the default serialization that we'll be using today, actually. Now, okay, let's think of another example. Socrates taught Plato. That could be expressed like this, where now I'm going to touch upon this prefix above. This prefix defines essentially where this relationship taught is described. What does that mean? Because right now, when we read this as humans, we kind of know the word taught, what it means, right? But the machine doesn't really. So the idea is that at that location, somehow, example.org doesn't exist, or maybe it does, I don't know. But it definitely doesn't have what we need. The idea is that somewhere over there, there's a some very rich explanation of what thought means. And another way to write it down is JSON-LD. So, and here, why I find this interesting, now we're actually not looking at a kind of a entity is of some type, but we're actually seeing two entities, two people, Socrates and Plato, and therefore you will actually notice them in the JSON object because they have distinct IDs. And it's a little harder to see that this is a triple here than here, but it is. Ultimately produces the same outcome. So this is how you write the data before you put it in the knowledge graph. This is just, if you wanted to send me a file, you would send it in some format like this. That's why it's called serialization, when you take some data and you put it in a file and then you have to pick a format, right? Another way to write this, a better way to write this, is to actually have this thought relationship somehow represented. And then you can do one of two things. You can go and explain it yourself and invent the whole concept of teaching and write it down somehow in even more complex ways, or you can basically build on top of what others have defined. And one such place is schema.org. That's a website that basically contains a lot of different types, and we'll jump on it in a bit, defined by actually a consortium of major search engines. So it was Google, Yahoo, Yandex. It was actually international collaboration. And they said, OK, we have to find some common way to help people label their websites so that our search engines can index them so that our search works better. So even though they're competitors, they came up with this joint schema. And why would people do it? Well, because if you label your website well, you will have better rankings in the search results, or in the search engine optimization SEO world, right? So basically, if we can also use schema for non-websites, and in this case, we can say, OK, Socrates is actually a person, which is defined very strictly as schema person. He has a name, and Plato is a person and has a name, and then we have some relationship that we actually express as an education event, because that's how schema.org models this type of relationship. It doesn't look perfect. I wish there was like a relationship thought, because this looks a little bit too complex, if you ask me. And I don't see teaching being an event. Teaching is a bit more longer-term thing. An event to me sounds like, I don't know, something that happens in a moment or like in a day. But I guess this wasn't a day or like a snap. So what we can see here immediately is that actually this schema that we use really defines the worldview, or as we call the ontological worldview in knowledge graphs. So I mentioned this word ontology, and I'll try to explain it. Basically, ontology is a way to describe the world, and schema.org is one of these ontologies. So essentially, they contain vocabularies, like what type of things we want to model in the world, how they relate. So if it's buildings, we're going to talk about things like doors, materials, all kinds of things relevant for buildings, and maybe we won't use like things that are important for sports, maybe. But maybe we would do for a stadium, for example. So if we're talking about a game, maybe it's something else. So generally, you want to have an ontology that describes a domain of knowledge that you're interested in, or a domain in the world that you're interested in, which you would build your world model on. And then basically machines can use that, and people as well, to have some consistent worldview. What is great about it, like I said, these search engines, they've used the schema.org thing for quite some time, is that they have interoperability across different applications and data sets. And basically, ontologies are one of the kind of main differentiators that take knowledge graphs up in that pyramid that we've seen. So they're no longer in the realm of data, because technically you could take some JSON and you could have a bunch of key value relationships and sort of describe something, but normally when you do so, you don't have strong types. You don't have such a rich explanation of what actually is being talked about. So that's not necessary maybe if you're building, let's say, an app that only you will use. And then I don't know, you need to, let's say, represent users in your app. So you need a username, maybe like first, last name, email, something like that. For that, people lived without knowledge graphs and ontologies and it's okay, like it works. But when you get into this data sharing scenario and when you want to build something richer, ontologies are great. So actually you move into the vertical direction towards the knowledge area in the pyramid. And like I mentioned, schema.org is one example, which is really more about web entities, people, places, events, things like that. There's another interesting one that's called FOF, or friend of a friend. And it's really more about people and relationships. So you can model social media through FOF, for example. But you wouldn't use it for something like buildings, for example. What is cool is you can combine ontologies. You can use 10 all at once. There's no problem. As long as you use them, you get this super rich explanation. And actually what happens is in the actual names of the properties, this prefix that I deliberately waited to talk about indicates the ontology. So basically the machine can read this and be like, aha, it's schema name, what does that mean? Let me check the prefix, aha, it's over there. That's the description of whatever this thing here is. And then the machine can go and understand it and go deeper. And let's actually go to schema.org, just so it's not all so abstract. If you go to the website, you will see basically a bunch of stuff, but I'm going to jump into the schemas right away. And for example, I'm just going to pick, let's say, a person, because we were looking at that. So here on this website, not that you would be really engaging yourself too much with this, but here we can see an explanation of how they've defined a thing typed as a person. And then you can see all of the potential properties that are part. So it's a person, alive, dead, undead, or fictional. That's a super simple explanation. And you have a bunch of things. A person can have an address, an additional name, an award, like a Turing Award, for example, or children, or So there's a lot of these things. Fax number, whoever uses that anymore. Gender, occupation. So basically, they defined a certain worldview of what a person needs, like a weight and who that person works for. And you can see what's interesting here. Let's say we stick a little bit here. When you have a property person works for, let's say, Amazon, what's cool about knowledge graphs is you can model that relationship without just saying, okay, this is going to be some word that happens to be Amazon. You can actually say, wait, this relationship has to point to something that is of type organization, which is another schema type. So if I go in here, you will actually see that an organization has its own address and all these things. So basically, this schema.org has defined a lot of these types for us, and which is great because we don't have to do it. And ideally, we use ontologies. That's kind of the whole dogma about ontologies is please don't build your own if you don't need to. But sometimes you need to. What's also really cool is when you look at this thing, I'm going to zoom in a little bit, an organization is kind of a type of a thing. So let's go see what is a thing. A thing is the most generic type of item in this ontology. So basically, organizations, people, whatever, they inherit the properties of things. So just like in object-oriented programming, we have the ability of inheritance. And that is super useful because then once you identify things like description for a thing, then everything that derives from the thing is going to also have this ability to have a description and so forth. So it's like super richly typed data, basically. Okay, moving on. I have about 15 more minutes, which is not enough, so I knew I'm not going to be as fast as I hope. But so far, okay, any questions? Should I move faster? Should I move slower? Am I boring you to death with this super tech stuff of knowledge graphs? Okay, so if anyhow, the takeaway here is we're moving past data. We have somehow very nicely structured this information, and we have these ontologies that describe what this information is, so kind of like a worldview. Okay, now the kind of the punchline, why would we do all this hard work? Well, it's for machines to understand it, but also for machines to be able to reason with it. So let's do a Socrates example. If Socrates is human, and a human is a subclass of something we define mortal, let's say that's the knowledge we have in our graph. If we add a rule that says, if some x is of type A, and something of type A is subclass of type B, so basically, like person is a subclass of thing, or in this case, human is a subclass of mortal, then we can conclude by basically first order logic that X is also of type B. So basically this is a rule. If you have the knowledge and you have the rule, then the knowledge graph by itself will infer a fact that wasn't part of the knowledge, which is that Socrates is mortal. This is kind of the most simplest example, and but I like it because of the simplicity, because the point here is that essentially, think about having a lot of knowledge in a graph, think about having a lot of rules, and you will see this happen a lot more. We'll have a graph infer something, but not by hallucinating, not by guessing the next word as we just did a few moments ago here, but actually by applying rules like we do in math or in physics. And this is the symbolic reasoning we're talking about. So couple that with LLMs, you get something very powerful. How do you train such a system? Well, you don't have to do another training round where you have to run a bunch of GPUs for a very long time, spend a lot of energy and money. All you do is add a rule. So these rules basically define, again, what's your worldview. So if you learn something new about the world, then you can add that rule, and the knowledge graph, the AI basically knows more. You trained it, you just added the rule. Now, what does this have to do with the DKG? Well, the DKG is a decentralized knowledge graph. So that means we need to somehow take what we've seen and we need to package it so that it can be used in a decentralized way. To package that RDF that we've seen, we use something called knowledge assets. And these knowledge assets conceptually have knowledge inside of them, so RDF, out of which we often produce some form of vector embeddings. That's the neural kind of representing data, which is super useful. That's what LLMs do. We have some cryptographic proofs. I'll dive into them. And then we have something called the Uniform Asset Locator, or UAL. And basically, these four things make it up. So imagine this hexagon containing a bunch of knowledge, but it's somehow provable, and it somehow has some form of unique ID. What does it look like very precisely? Think of it as containing that knowledge. So this is a schema.org description of this conference. So this is the Decentralized Knowledge Graph conference. It has this start date related to this website. And this thing has an ID, DKGcon at AI. I use the website. It's a type of event defined as in schema.org. And its location is another object, which is a place. And this place is defined here. It's the city of Ljubljana, and its postal code and everything. And actually, I left this out. This was 2 years ago. We were at BTC, because it kind of looks cool that it's BTC as Bitcoin. But anyhow, so this would be, let's say, a set of triples noted down as JSON LD. That would be the knowledge. Now, okay, what happens with this knowledge if you push it into the DKG? Well, we obviously want to know who made this knowledge, who introduced this to the DKG. For that, we use this knowledge token. And that's actually, I'll explain it a bit deeper, but that's a crypto token sitting on the blockchain. So the gray parts are on the trust layer. They're sitting on the blockchain. The blue parts are in the knowledge layer, in the DKG. And this knowledge token is a token like any other NFT token or a non-fungible token. I'll explain that in the next slide. But it's there to represent the ownership of that record. So that means if I create that in the DKG, there will be a token created for me. I will be able to own it with some wallet. I'm not sure how much you can see this, but it shows a blockchain address. So a wallet like holding any other token. And with that ability, I actually now own this record. That doesn't mean I own the city of Ljubljana, but I own that record. And with this ownership, I actually can do a couple of interesting things. I can, for example, as any other thing I own, like this phone, I can sell it, for example. Or, even more interesting in this case is we can update this graph. So only I can actually update if I'm the owner. And Ben cannot because he doesn't have the token. But if I send Ben the token, now he can do it. So we basically use the blockchain primitives to implement some interesting policy of how we can update or really own the state of this graph. Now, what does this word state mean? Well, let's imagine I wrote this down and I wanted to change this BTC to actual location where we're here in this beautiful jazz club. I could do that as long as I have the token, but that would change the data. So we want to track that change somehow. And to track that, we use something called state proofs. And they look kind of like this, like a bunch of gibberish. But actually, they're not gibberish. This is something called the Merkle proof. And I'll explain that in a bit. But basically allows machines to somehow produce from this data this. It's basically a hash. If you heard about hashes, it would take this, it would hash it, it would produce this. So whenever I update the content, the hash will change because I will produce a new one. And this hash we will store on the blockchain. So whoever gets in contact with that piece of information can see, that's the person who owned it at that moment in time. And that's the state it was in at that moment in time, including right now. And you can always compare it to that hash. So if somebody gives you somehow through the internet a distorted version of that, somehow different truth than what I posted, you will always be able to check it on the blockchain, your agent will, to see if the hashes match with this content and see like, okay, this really comes from Branimir and it wasn't changed along the way. Kind of like in some sort of man of the middle attack, let's say. So that's where we use blockchain. We don't store anything else on the blockchain, just these things. Why? Because blockchains are incredibly slow and unscalable, even the most scalable blockchains. They're not designed to store a lot of data. They're especially not designed to do knowledge graphs. They don't have query languages. They don't have the right structure. But they're really good as trusted machines. They're like your truck that you would use to take gold into a bank vault. But you're not going to use that truck to go to a store to buy milk because it's too much, right? It's too slow and it takes too much gas and all of that. So basically the point is blockchains are super useful, but you should use them in a sort of minimal way. Try to use it as little as possible to get the most value out of it for the least amount of cost. Now, when we get this token and this proof, we actually get something called a uniform asset locator, which looks like this. And this is a special type of identifier. It conforms to the URL spec or URI spec, which is basically the kind of the identifiers used in knowledge graphs. So when you see that DKGcon.ai in the @id field, that's the URI or URL, which is kind of a weird thing because it's confusing. Technically, it should be an IRI. So there's like, I told you 3 terms from the semantic web world, which I can admit, honestly, I can remember what they are, I can tell you the shorthands, but how does that... Hello? That was a weird sound. Okay, super, great. We're back. So anyhow, my point is that's what people decided to use, web addresses, because that makes sense. You can own a web address, you can buy a domain, in the semantic web, again, the idea was to make this web of data rather than web of pages, as in the World Wide Web. Well, we take the concept one step further. Instead of going and buying domains from the usual places, which are somewhat centralized entities, something that we don't really like in Web3, we make these on our own. So this sits in a smart contract. Whenever you create a knowledge asset, an NFT is minted, For those of you who know about NFTs, this is actually the token ID. So we didn't like invent anything special. We just said, this is a decentralized identifier on the DKG on a blockchain called Base. In this smart contract, there's that NFT. So if somebody sends you this, and none of the other stuff, it's kind of like they sent you an URL for this and a URL for this. So basically, it's a self-resolvable, ownable identifier that is globally unique. Nobody can have the same thing because it's managed by a smart contract, and you own it. And you can do all the usual cool stuff you can do with URLs, like you can add a hashtag or the query string question mark thing, and basically you can point to something here, like kind of like let's say at the start date. You can do hash start date, and you could technically build a system that will, instead of returning this whole thing, just return this, just like on the web. So that's kind of the anatomy of a knowledge asset, and all of these knowledge assets obviously sit in the DKG. So we basically, in summary, we took RDF, we wrapped it so that we can implement ownership, provenance of this data on the blockchain, and for that we have identifiers so we can capture both these records, which technically sit on two different layers. So the URL is kind of glue between those two. Yes, go ahead. Mm-hmm.
With DIDs, are you also utilizing them for selective disclosure, like the ability to?
That's an amazing question. I have an answer that comes in like 2 slides. Is that okay? Super. And then please jump in if I didn't answer it fully. But for the folks who are not really familiar with these NFTs, a little bit more info, and I'll jump to exactly that question. So NFTs, again, are these non-fungible tokens. We use them to implement URLs, and they're unique on-chain identifiers, which enable ownership, provenance, and versioning. And basically, like I said, we can send them around. There's a whole ecosystem of things called wallets, where you can keep these tokens, just like you keep your money, cash, or credit cards. You can keep these NFTs. And with this capability, now you can publish updates and create associated value flows. And essentially, this NFT is kind of a verifiable handle that agents can then use. So, and ultimately, cryptographically use them to cryptographically verify what's in the DKG. You can transfer them. You can build data markets. Maybe you've heard of NFTs before as like people selling these pictures, and there's this whole dilemma of how do you own the picture if you don't really own it, because somebody can change it, delete it, or whatever. Outside of our world, because we're not talking about monkey picture NFTs here, which we're talking about ownership in the knowledge graph. So basically, anytime you get something from the DKG, you'll be able to see who the owner is, and then you'll be able to do all of the things that we mentioned, verification. But ultimately, we didn't want to go outside of the standardized system. So you can use all of the other NFT ecosystem tools and things, wallets, bridges, all of these things together with the DKG in the same way. So you can build an NFT marketplace just for knowledge, for example. Now, knowledge assets, that one hexagon, they connect into graphs. So not only can we connect, can we make like super rich graphs in the traditional sense as in centralized knowledge graphs, but we can actually now use this other rich information. We can use URLs to point to creators, to publishers, to events on the blockchain. So it's a kind of another dimension introduced into the graph, and we can make super interesting structures where for each of these entries, we can consider them as, let's say, one type of memory of an agent. Imagine an agent doing something on Twitter, let's say responding to you. They could store that as a knowledge asset in the DKG. And then later, when they speak to you again, they can go inside of this memory and say, hey, what did I speak with, I don't know, Eleonora about 2 months ago? And you could ask it, hey, remember that time we spoke about my favorite food? And it will actually go and find it in the graph. It won't keep it in some sort of semi-structured memory, which is something we often see when people implement agents without knowledge graphs. They would put data somewhere, like in a database. Nothing wrong with it, they're just less powerful. In a database or some sort of document, and then they search it through vectors, and they have this sort of fuzzy search thing, where here you can be very, very precise, and the agent specifically can be. one of the reasons knowledge graphs haven't been so hot for so long because they're really hard to do. But luckily today we have LLMs, so they help us. So a bunch of these examples that I've shown you were just generated by ChatGPT this morning. So it helped me quite a bit. So basically what I'm trying to say, the cost of building knowledge graphs went down significantly. What about privacy? So, okay, it's great, we build this decentralized knowledge graph. Everybody pulls their data in, kumbaya. Well, not kumbaya, we need to maintain privacy in some way. So these knowledge assets implement that too. So you can add triples data inside of the knowledge assets, and you can designate which ones are private, which ones are public. And when you create them, you specify it. If you forget to specify it, the system will assume you want to create private knowledge, just to make sure that you don't leak something publicly that you didn't want to. What does private knowledge mean? Well, now we get to this notion of the network. You would be, with the DKG, interacting through some form of node, and a few minutes from now, you will be setting up a node on your machine. This node, in itself, contains a graph database. So all of the private triples, the private knowledge that you don't want to share with the world, would stay on your device. All of the public triples will go into the network. And those public triples can be seen by others. Consider it kind of like a website. You have a website and there's like a paywall on the website. So the public data, search engines can index it and do all of the cool stuff. But if you want to access something that's private for that website, maybe you have to pay. So that's kind of the analogy here. And now comes the answer to the question about selective disclosure, which are these Merkle proofs, and that state root I came about. So bear with me for a bit more of the tech. What is a Merkle tree? This is a very interesting concept where basically we would take something like text, in this case ABCD, and we would hash it. Hashing is a very interesting cryptographic type of function. You give it some content, like, I don't know, a word or a whole file or whatever, and it produces a thing like this out of it. It looks like gibberish, but it's not. But what's interesting, let's say I took this and I produced that. If I just change one letter here, this whole hash will change. But every time I use the same content, it will produce the same thing. So that's why people also call them sometimes fingerprints. Just like each human has a unique fingerprint, each set of data or sequence of characters will have a unique fingerprint. You change one character, it changes completely. Now you can build some really cool things with it. Imagine you hash these things together. So A, B hashed, C and D hashed. And then you take two hashes and then you hash them together. And then you do that and we build a whole tree and you get something called the root hash of this Merkle tree. What's really cool here is that you can do something called proofs. So selective disclosure. Imagine I had this information, A, B, C, D, F, G, H, and I made it private in the DKG. But I wanted to share with Professor Bob, let's say, for some reason, this value D, he wants to see it. So I can show, look, I know this value D, it's inside of my knowledge asset, but I'm not going to share the rest of it with you because you don't need to know. Let's say a case would be you're entering a bar and you need to show that you're over 18 or 21, depending on where you're from. You will not need to disclose where you live, for example. So instead of showing your ID that maybe says where you live, you can just show, look, I'm over 18. And that person doesn't need to know more. Simple example that you can we can all relate to. We're all at some point under 18, right? So how does this work? Well, it works like this. If you want to, let's say, share the value C, what you need to give to the other system is just 3 values. You need to give it actually a hash of this, because when you have a hash of this and a hash of this, you can then produce the hash of this. To produce the hash of this, you need this value, which is another hash. And to produce that final thing, you need one more hash, which is that. So it might look a bit complex, but basically with these couple of values, we can rebuild that hash up there. So I can send Professor, look, I have C, and here are a couple of hashes, and you yourself or your agent can compute that ultimate root hash, and it's going to match what you'll see on the blockchain. So in that way, think of this, but applied to very large graphs, like thousands of entities. we can do selective disclosure, and we can show, look, this thing is inside of my graph, and I can prove it to you. And you don't have to trust, it doesn't have to be trust me, bro. This is something people from the blockchain space, I'm sure, have seen before or kind of know about. It's not like that we invented some magic here, but it's very useful. And then there's even things to go further from that, like zero knowledge proofs and things that are super exciting. So, but we don't have time for all of that, and I'm already over time. So I have like 1 or 2 more slides to finish. But basically, I want to just go back to this concept of the network, and I'll share an example. Now, let's go back to the real world. This is how Swiss Railways uses OriginTrail. They have a bunch of partners who are running nodes, and they share data. So they have a certain ontology they follow, or standards, and these are in specific GS1 standards. Not going to go too deep into that. There's a whole webinar, by the way. If this is interesting, you can scan and watch and hear them talk about this. But for the purposes of this presentation, what they're really doing is they're creating knowledge assets, and all of them pretty much private data. And then when Swiss Railways, SBB, needs to know where their train is right now in France, because they don't have their systems in France, they contact SNCF, which is the French railways, which has sensors on the tracks, and they do all kinds of things. They even try to find which wheels are the ones they should change because they're deteriorating, they're going to break. And obviously, they cannot do that from Switzerland if the train is in France. And so basically, for them, this is a no-brainer that they need to exchange information, but they cannot just exchange everything all at once without some sort of privacy and access control. So when we think about OriginTrail, we think about knowledge graphs that live across a network of machines where each one of them has its own knowledge. So kind of like, just like the internet is a web of computers, this is a web of knowledge, and it lives all over the place. Another way to look at this is we have this distinction of core and edge nodes. We talked about it yesterday. Edge nodes live on edge devices, so the new one you will be launching on your edge device, which is the laptop, but laptops, what we do with them, we shut them down, right? Well, for the things that need to be operating for the DKG to be available all time, we have something called core nodes. Those live in the cloud. They're like, they run all the time, and basically they're actually incentivized to do it. How do we incentivize the DKG nodes, and why do we do it? But, well, again, coming back to that idea, we want agents to access that memory, and they do that through something called decentralized drag. So they need to retrieve information, but from a bunch of nodes. They don't necessarily know where the data is. So we need some way to address the data, and that's why these UALs are super useful. And by the way, edge nodes don't have to be just on edge devices. As you can see, there's a couple of examples of things like Amazon Neptune, for example. You can build an edge node there that doesn't have to be highly available and run all the time. But if you would run a highly available node, you would be helping the system run, and anybody can run nodes, by the way, and therefore you would be sharing part of the fees that the system is collecting. Because every time you want to write something into the DKG, it costs a little bit. You have to pay a little bit, but not to us, or only to the people who are running these nodes. And for that, you use the track token. So the track token is basically the economic primitive of this decentralized system. What does a node look like? We touched upon this yesterday. I think maybe in the next presentation we'll go a little bit deeper, but super quickly, again, every node will have its own graph database and maybe other databases like a vector database. It will have what we call the node engine, DKG node engine. This allows it to speak with other nodes. This is like your networking card in Ethernet. Then you have your left and right brain, the reasoner semantic one, the LLM, and then you can build your own stuff, plugins on top of it, which you expose through either an MCP server, we all know MCP is cool, right? Or classic API. And then you have a UI, and then you can attach agents, and relatively soon you'll be able to run multiple agents on the DKG. So for example, you could build an ELIZA agent, what we'll see later, and you could use it with this node. You just install the thing next to this. And basically you're plugged into so this is kind of like your computer when you hook it to Wi-Fi and you're connected to the internet. That's the node in the OriginTrail world. So if you want to build with the DKG, you would install this, and this is, by the way, open source. You can modify it, do whatever you want with it, extend it. One last thought here, and I know I'm a bit over time. We don't say which graph database you should use. We are, again, according to the principle of inclusiveness, we want to let you pick what was best for you. Who are you? Well, maybe you're an enterprise, and maybe you really love AWS, and you're probably going to pick AWS Neptune because maybe all your stuff is already there, and you have some great relationship with them that, I don't know, they gave you a discount or something. So if that makes sense. And the OriginTrail supports Neptune since, I believe, half a year ago or something. If, let's say, you don't have those needs, maybe you just want to play around, you can plug in some open source RDF database. And today, a default one will be installed for you, which actually is the precursor to Neptune called BlazeGraph. It will be just installed on your computer. You don't have to think about it, but it's going to be there. My point being is, as long as it follows these W3C standards, you can plug anything in. And the ambition is that you can plug in an existing graph, like Google can plug in an existing graph, or something that Ben created. He already has a graph, so he doesn't now have to go and copy this whole thing into the DKG. Ideally, he can just plug it in here, and this node will somehow automatically create knowledge assets out of this and make it easy for him. That's the plan. We don't have this yet, but that's coming up in the roadmap. I would not do justice to the trust layer if I didn't mention it a bit more, because we went super deep in knowledge graphs, but for people who are a little bit more confused about what the hell this blockchain thing is and how does it work, it's based on a very adopted virtual machine called Ethereum Virtual Machine, EVM. The language used there is Solidity. There's a bunch of standards we use there as well. I won't go too deep into it, but basically, this layer also, we try to be as inclusive as possible. We track, basically, on this blockchain, we track the provenance of all of the knowledge in the DKG, who owns it, what are the state roots, but we also implement these economics. So if you're going to use the DKG and you pay these little fees to use it, as we mentioned, those fees are going to be shared among the nodes who provide the services. So it's all managed by the blockchain. There's no company in between. There's no bank account. It's all happening on chain. It's all happening on tokens, which means anybody in the world can turn in an OriginTrail node and can start supporting this network. And because they're contributing the resources of their machine, wherever it is, anything from a laptop to like a full-blown bare metal server, they would be getting some economic return from these utility fees. We also use the blockchain to track who has published how much knowledge into the DKG. That's very important for us, pardon me, because we basically want to incentivize people to share knowledge. So if there's a node publishing more knowledge, it has a bigger propensity to earn more fees back. We want to incentivize against people who are not just running nodes and run and forget, but you're actually adding knowledge to the system, which is the primary reason why we're building this. There's also something called staking, which is if you are part of the ecosystem, you're not running nodes, but you have a share of tokens, you can either use those tokens for publishing, but if that's too much for you, if you're not a builder, you could just be invested in it, and you could do something called staking. You could stake these tokens actually on other nodes, and in that way support those nodes and share a piece of those utility fees with them. Also, some things that the blockchain helps us achieve is unified system clock, which is generally very problematic in distributed systems. We use something we call epochs, and we track the nodes and their identity, but obviously in an anonymized way, because we want to associate how much they published and how much they earned. We need that for implementing it. So, and finally, it implements also something called DKG Paranet registries, which is the last thing I promise I'll talk about. Knowledge paranets are your way to create collaborative DKGs on the DKG. You can say, I want a knowledge graph on topic, like, I don't know, sports. And you could be an operator of that graph, but you can open it up for many different people to use. And you can incentivize those people using the neuro token. As I've been kind of circling around it, there's actually a customized blockchain for OriginTrail, which is called NeuroWeb, and its whole point is to reward people for what we call knowledge mining. So just like Bitcoin mining, you turn on a machine, you mine Bitcoin, and you get some Bitcoin in return, maybe. Here, the idea is you add some knowledge into the system. The paranet somehow, using those rules and setups, figures out, is this knowledge valuable to me? Does it maybe go against what I thought? Let's say we have a football, soccer knowledge graph, and somebody comes and says something, I don't know, wrong. Like, for example, Maradona is playing for Ljubljana today. Is not, I believe he's not even alive anymore. So anyway, you could make that statement, and the DKG will say, okay, you said that. That doesn't mean it's true. It's on the paranet to decide if that knowledge is something paranet operator and its software, the services that they run, and the ontologies and all the clever stuff to decide if this knowledge should go in or not. If it does go in, if it passes all these checks and systems, then you would qualify for these mining rewards. So the idea is that Neuro is used as the other token to incentivize people to create new knowledge in these types of paranets. Again, another reason for paranets is we don't want everything in one big knowledge graph just like that. We want to, again, go by domains, use specific ontologies, and in these domains, everybody can create their own thing. And then we can pick if we want to use that thing or not. So I don't know, maybe there's a CNN knowledge graph, and there's people who don't like CNN for their reasons, and they can just have their agent ignore that paranet because it comes from CNN. Or maybe you're a particularly big fan of Stanford. I don't know. You're going to use the Stanford knowledge graph, and you're not going to use whatever Ljubljana University knowledge graph because you have a beef with them or something. So that's kind of the point. We have these ownable small entities, knowledge assets, and we have this bigger ownable graph, but where they're still collaborative. So yeah, I'm going to be quick. I already went through this. This blockchain is where basically you can ask for your paranet or from the community to support your paranet with a certain amount of Neuro tokens. So to conclude this long presentation, this is the hierarchy we're talking about here. We started from triples, the most minimal thing, entity, relationship, entity. Socrates is human. We went into knowledge assets. We packaged that up into something ownable and trackable and with trusted proofs. We combine those knowledge assets into paranets, and multiple paranets make up the whole DKG. And it's all running on a decentralized network of nodes. I hope that wasn't too much. And it really still is skimming on a bunch of topics, so it's somewhat shallow. But if you want to learn more, the docs are here. We're here. You can ask us.